In the real world, we don't talk about accepting states. Instead, we let the output do the talking for us. We have been talking about finite automata and all the things that it takes to define it and the ways that we represent it, including transition tables, state diagrams, things like that. Now, what are some of the things? Well, let's just do a real quick review. We've got a state in a state diagram represented with a circle with the name in it, an initial state defined with an arrow going into it. We had accepting states that had two circles around it. We talked about transitions that are arrows directing us from one state to the next state. And associated with each one of these arrows, we have an input, something that was defined by an input alphabet. So for example, if we had the binary numbering system, as binary is our alphabet, then a 1 might be one transition, a 0 might be another transition. And then we talked about deterministic automata, which meant that whenever you're in a state, then based on our input, we had exactly one transition to go to. And then we also had the transition function, typically represented with a lowercase delta. And the lowercase delta took whatever state we're in, so from the states, and based on whatever input we had, so that was the input alphabet, it mapped us to another state. And we've done all this, but now what I'm going to talk about is the fact that we really could use some output. In other words, this is all theory. What are we going to do when we start talking about output from our system? For example, what good is a finite automata that defines how a traffic signal system works if we don't have the red, yellow, and green lights to tell us whether to stop, go, or use caution? What good is a lamp that is controlled with like an IoT device that could be controlled with our phone or a switch on the wall? And that microprocessor inside is basically implementing a finite state automata. What good is it without the output of the light bulb? Even when we're starting to start talking about regular expressions and whether or not a sequence is a member of a regular set, it's either a member of the regular set or it's not a member of a regular set. But there's actually a third condition. We haven't figured it out yet. It could be, but it might not be. And so all these outputs need to be represented some way so that us as the viewer, as the user, can actually interpret what's going on inside the machine. That's what we're going to talk about today. Now, once we take our finite automata and associate an output with it, we get what is called a finite state machine. Sometimes it is referred to as a transducer. All right. A real-world implementation of the theory that we've been talking about so far. Now, there are two types of finite state machines. There is the Moore machine and there is the Mealy machine. The Moore machine basically says that it is the current state that drives the output. The Mealy machine says it is a combination of the state and the current input. This drives our output. Two different machines. They have characteristics. There's benefits of one over the other. That's what we're going to talk about next. Now let's start out this discussion about output and Moore versus Mealy by using one of the examples we have been talking about already. Remember, I had a regular expression that was, it was following the flips of a coin, heads or tails. And what I said was I could have any sequence of heads or tails, just any random sequence of heads or tails. But if the last two coin tosses were both tails, then we had a member of the regular set. So any sequence of heads and tails and heads and tails, but if the last two were both tails, we had a string that was a member of the regular set. And what we talked about whenever we were looking at our finite state automata was we started out in our initial state. We'll call this Q0. And that meant we don't have anything. Well, we could have any sequence, but the last two or the last one toss did not result in the tails. If we got a coin toss that was a tails, it took us to state Q1. If we got a coin toss that was a heads, it kept us in state Q0 waiting for a tails. Now, Q1 basically says the last coin toss was a tails, but the coin toss before it was a heads. If we get another tails, it brings us to state Q2. Now, in our discussion of finite automata, I would actually put 2 circles around this to show that it was an accepting state. The point is that now we're going to use the output to show what the condition of our state machine is. Now, in Q1, if we get a tails followed by a heads, well, that brings us back to this condition where last toss was a heads, we're waiting for 2 tails in a row. Now in Q2, if I get another tails, what that means is, and as long as I keep getting tails, that just means that, yes, the last 2 tosses have been tails. But if I get a heads, it brings me back to our initial state, to our, we don't have any tails. You know, the last one was a heads. Now, what I said was we're going to take away this idea of using accepting states and use output to the user in order to show that, the condition of our state machine. Now, let's assume that I've got a light bulb, and my light bulb is just going to be on if we had the last 2 tosses were a tails. It's going to be off if the last toss was a heads, or if only the last toss was a tails. If it was heads, tails was the last 2 tosses. Now, when we're talking about a Moore machine, the way we represent a Moore machine in our state diagram is to include, since remember, the Moore machine takes the current state and maps it to our output. So the state identifies the output. The state identifies the output. So the last one was a heads. No, the light bulb is going to be off. The last 2 tosses, we had a heads, then a tails. Light bulb is still going to be off. The last 2 tosses were tails. The light bulb is going to be on. And so that gives you an idea of, well, just watch the light bulb. You know whether the last 2 tosses were tails. Now let's look at a state machine that is going to do this, except it's a Mealy state machine where it includes both the last state or the current state and what the current input is in order to define our output. Let me show you how this works. This is going to actually be a different state machine. We're going to start again with our initial state, Q0. Now this is a Mealy machine. And as I said before, it's going to take our current state along with our input in order to figure out what our output is. All right. Now, from Q0, this is the initial state. The last toss was not a tails. As long as we keep receiving heads, we're going to stay in this state. But the other thing we want to do is say that also, if we're in Q0 and we get a heads, the light bulb is going to be off. So notice now we have a slightly different representation here. Up here, the output corresponds to the current state. Here, the output corresponds to not only the current state, but what the current input is. All right. Now, if I get a tails, remember, this still, if we get a tails out of Q0, that just means only the last coin toss was a tails. And we still shouldn't turn the light bulb on. So if our current state is Q0 and we get a tails, we still want to leave the light bulb off, all right? And this brings us to Q1. Now, if we're in Q1, we also have to figure out what happens if we get a heads, and we also have to figure out what happens if we get a tails. If we get a heads, we go back to the state that says, hey, last coin toss was a heads. And so we leave our light bulb off. But here's where it differs from the Moore machine. Notice that that's really exactly the same as what we have up here with the Moore machine. But the Mealy machine says if the last toss we get out of Q1 is a tails, we're going to turn the light bulb on. And that's our fully defined Mealy state machine for this, looking for the last two tosses to be a tails. So the way this works is every time I get a heads, I'm coming back to Q0, kind of the reset state. If I get one tails, it brings me to Q1. But if I get a second tails, I'm going to stay in Q1 and turn the bulb on. Notice, only two states. But this is a little bit more complicated in terms of being able to design it. In a future lesson, we'll talk about the steps it takes to convert a Moore machine to a Mealy machine. But for now, let's just do a couple of more examples so we get more comfortable with not only the representations, but the operations of Moore versus Mealy. Before we move to another example, let's talk a little bit about another representation. Rather than looking at the state diagram, we can also do the state transition table. Now with the Moore machine, the transition table looks a lot like the transition tables we've used before. You start out with a current state, right? And we had three of them. We had Q0, Q1, and Q2. Q0 was our initial state, our beginning state. And then what we had was, where do we go if we get a heads? Where do we go if we get a tails? Well, if we get a heads, remember everybody goes back to Q0 because Q0 was the state that said, hey, we're looking for any tails. We got nothing right now. If we get one tails, we went to Q1. If we are in Q1 and have one tails and get a second tails, we go to Q2. If we're in Q2, as long as we keep getting tails, we stay in Q2. Now, I've left some space here because for the Moore machine, I'm also going to have the output. So it's going to associate the state with the output, the state with the output. And remember, the only state where we had turned the light bulb on was for Q2, where we got two tails in a row. Otherwise, it's off. All right. Now, our state transition table for the Mealy machine is going to look a little different. What that's going to do is it's actually not going to add another column. We're going to take the current state, and remember there were only two. There was Q0 and Q1. Q0 being our initial state. And then we had to figure out what happened if we had a heads and what happened if we had a tails. Now, I'm not going to add this last column because what is defining our output is the current state and the input. So the current state and the input, I'm going to put both the next state and the output in that column together. So if I was in Q0 and I got a heads, I stay in Q0 and continue to leave the output off. And remember, that's true for Q1 too. If I'm in Q1, any state I get a heads, I'm going back to Q0, and I'm going to leave the bulb off. Now, if you remember, when I was in Q0 and had a tails, that brought me to Q1, but the bulb was still off. If I'm in Q1 and got a tails, that kept me in Q1, but I turned the bulb on. And so a slightly different way of representing the transition table. Remember, the Moore machine says I'm going to have the state is the only thing I need to define my output. The Mealy machine says the state and the input are required in order to define my output. I had another regular expression that we were looking at before that said, if I get a string that starts with a 0, has any number of ones, and then ends in either a 1 or a 0, I've got a member of the regular set. And so we've got examples like 0, 1, that's a member, 0, 1, 1, 0, 1, 1, 1. And then I've also got members like 0, 0. Okay, that would be 1 with no ones in between. 0, 1, 0, 0, 1, 1, 0, and so forth. The state diagram was a little bit more complicated for this guy. We did once again start off with an initial state. We're going to call this Q0. Now, what happens is I have to get a 0. So if I get a 0, that's going to bring me to Q1. All right, that's my input. If I get a 1, I'm going to come down and I'm going to call this Q4 because I'm going to just make Q4 Yes, I know how many states I've got. I wanted to make Q4 my last state, or this error state. So if I'm in my initial state, I get a 0, things are still possible. But if I'm in Q0 and I start with a 1, not possible, all right? So this one right here is the state that it's not a member of the regular set. There's no way that it can match this regular expression. If we get a 0 and go to Q1, it's still possible. Notice we don't know for sure yet. None of these patterns here are just a 0 by themselves. If I'm in Q1 and I get, let's say I get a 0, all right? So I get a 0 and a 0. I'm going to come down here to Q2, all right? Now Q2 is pretty much, I got this one, 0, 0. That's the only thing that's represented by that state. If I get a 1, I'm going to go to Q3. All right, and Q3 says I got a 0 followed by a 1. And so automatically I'm in this group right here. So a 0 followed by a 1. And I could keep getting 1s and it'll keep me in Q3. Now, if I get a 0 followed by a 0, there's no other way. I can't get any more characters, any more digits, and have it still be a part of the regular set. So if I get anything else after that, a 1 or a 0, then I'm going to this, it didn't work out state, right? If I'm in Q3 and I get a 1, and that means that, well, we got a 0 followed by a 1 followed by any number of 1s. And I'm going to be on this side of the patterns, right? If I get a 0 followed by any number of 1s followed by another 0, all right, that's going to bring me over to this side. And that'll be the only possibility is a 0, 0 with any number of 1s in between it. That takes care of 1 and 0 from Q3, 1 and 0 from Q2, 1 and 0 from Q1, 1 and 0 from Q0. Q4, well, once the pattern fails, it is always going to fail. And so we're going to stay in Q4. Now, and if you're interested, I did do a full video on how to do this particular state diagram. What I wanted to do was show you how the Moore machine works here. Now, the Moore machine is taking this and it's going to say, okay, in the bottom half of every one of these states, I'm going to associate the output. Now, remember, the Q4 is no. It is not a member of the regular expression. Q2 and Q3, yes. The pattern that brought me to these states, both of those patterns, yes, they're members of the regular set. These two right here, though, that's kind of a pending state or a possible state. So I'm going to I'm going to have to abbreviate it because I don't have a whole lot of room here. I'm going to call this P, N, D, N, G. Pending, okay? So P, N, D, N, G. All right. And so those two states right there mean we're not sure. So the output in this case, there's actually 3 different possible outputs that we could have. Maybe displayed to a screen or something. Maybe different light bulbs. Maybe a red, green, and a yellow for those. Okay. So it just depends on how you want your output to work. Now this is our Moore machine. But what does this guy look like in a Mealy machine? Remember, I said in a later video, I'm going to show you the conversion process. But right now, let me just show you the actual Mealy machine that results from this. In this case, once again, we have Q0. I can put my name in the middle of the circle because I don't need to leave room for the output. Because remember, the output's going to be associated with each one of the transitions that are coming out of the state. All right, so I'm in Q0. If I get a 0, we still have, this is a pending, all right? It's possible. We don't know yet. It's not yet, okay? I probably should have called it not yet. All right, so Q0, if I get a 0, not yet. But it's possible because all of our sequences start with a 0. Call this guy Q1. If I get a 1, however, I'm going to go down to Q2, and a 1 is no. We didn't get it. All right. So that takes care of 0 and 1 and the corresponding outputs coming from Q0. Now, Q1, as long as I keep getting 1s, well, what I've got is a 0 followed by any number of 1s. That is a yes. If I get a 0 followed by any number of 1s followed by a 0, it's still a yes. All right. So I've got 0 and 1 coming out of Q1. I don't have 0 and 1 coming out of Q2. Well, once you get to Q2, that means I've either completed this and can't get any more characters, or I started out with a 1 and it's not going to be it's not going to be a member of the regular expression. So 0 or 1 with a no. And there is our state diagram for the Mealy of detecting that pattern with output. So let's do a comparison real quick of Mealy versus Moore. Mealy typically has fewer states, all right? Moore, though, is easier to design. Mealy, if you have like a clock pulse or something that's taking you from one state to the next state, and we're not ready to move to the state, but yet the input changes, our output could change. For example, if I'm in Q0 and I'm waiting for a clock pulse to say that the next bit is valid, but the bit changes first, I may actually get a no or a pending prematurely before the state we actually change to the next state. So in a synchronous system, sometimes the Mealy will put an erroneous output for just a minute there. More easier to design, right? It makes more sense. And so that's kind of a comparison between Mealy versus Moore. In a future lesson, what I'm going to do is show you the steps it takes to take a Moore machine and convert it to a Mealy machine, so that one drawback, the one that a Mealy is a little bit more difficult to design, we take care of that.